Hello everyone, my name is Vitaliia-Anna Oliinyk, and today I will be talking about the implementation of my project concerning detecting propaganda in text data. So let's remind us what are the few common propaganda techniques. The red herring is a technique that is primarily used by introducing irrelevant material to the issue being discussed to divert attention from that issue. Straw man is a technique when opponent's position is substituted with a similar one but not exactly the same. Bandwagon is an attempt to persuade audience to join in and take the course of action because everyone else is taking the same action, even though it might not be true. Loaded language is the usage of specific words and phrases with strong emotional implications to influence the audience in some way. Exaggeration or minimization is either representing something in an excessive manner or making something seem less important. And appeal to fear or prejudice is seeking to build support for an idea by instilling anxiety or based on preconceived judgments. So, based on our conceptual stage of the project, we have divided it into two tasks. It's to identify propaganda on sentence and on article levels. Thus, two distinct data sets, one for each task, have been obtained, and two different models have been built. So firstly, we'll discuss article level propaganda detection. Firstly, let's take a look at our dataset. It contains 35,993 articles, each labeled as either propagandistic or not propagandistic. The unique article IDs are also provided, and data is stored in the format of tab-separated txt file. After loading our data and creating a pandas data frame for it, we remove the article ID attribute and now can take a good look at our data. Here is how it approximately looks. Next thing we have to do is to explore our distribution by classes, so how our text data is distributed as being either propagandistic or not propagandistic. As we can see, our data is not evenly distributed, and there's noticeably more non-propagandistic articles in the dataset. Next thing we have to do is to prepare our data, because raw text data is not a useful feature when it comes to machine learning models. So firstly, we have to convert every word to lowercase, so when vectorization algorithm is being applied, words like car from capital letter and car from small letter would not be counted as separate entities. Also, we remove punctuation, as it is not a usable feature on this level and can only slow down vectorization process computationally and confuse our classifier. And the third and final step is removing stop words. Stop words are words like here, there, has, so the words that do not have distinct semantic meaning and do not tell us much about the text. For this task, we are using an LTK inbuilt corpora of stop words to remove them from our dataset. Then the next step is feature extraction. The first thing we do is vectorize our text data. We use count vectorizer. This algorithm converts our data to a matrix of token counts. Each article is tokenized. It means that it's split by distinct words and vectorized by their respective count value in the data collection. The next thing we do is to perform a TF-IDF transformation. It's a statistical algorithm that stands for term frequency inverse document frequency. It's a method intended to reflect how important a word is to a document. TF is calculated by dividing a word occurrence by document length, while IDF represents how specific the word is, and computed by taking a log function of total documents count divided by documents that contain a specific word. We perform this algorithm on an already vectorized dataset. Next thing we do is to tune in the parameters. For this, we use grid search cross-validation. And the parameters we have is penalty that is being performed by ridge regression and solver LBFGS. So after training our data, model score is the following. It has 0.9 accuracy, while confusion matrix looks something like this. We can see that we have accurately predicted 6,102 non-propaganda articles and 690 propaganda articles, while the rest, 280 propaganda articles and 130 non-propaganda articles, were misclassified. The next task we'll get to is the sentence level propaganda detection. So let's take a look at our data set. It consists of 14,263 sentences. of either propagandistic or non-propagandistic nature. Dataset also contains unique identifiers for articles that contains those sentences and unique identifiers for the sentences on an article scope. Each sentence is provided with binary category, propaganda or not propaganda, so it's labeled. Labels and sentences are stored in separate files, each file representing either content or labels for a specific article. After loading and concatenating our values, we can take a good look at our dataset. It looks approximately like this. The next thing we do, as for the article level task, we evaluate how our data is distributed by classes. As we can see, the distribution is also uneven, but it's more even than in the previous task. The next thing we do is to do a feature extraction. To do so, from the sentence level dataset, I have decided to go with a more elaborate approach and do a manual data extraction, as well as use another vectorization algorithm. So these manual extraction steps include detecting quotation mark coefficients to catch the appeal to authority propaganda technique. Next thing is to detect glitter words that attract audience attention, such as patriotism, justice, truth, for flag wagging, and slogans propaganda techniques. Detecting intensifiers, that's words like very, extremely, incredibly for low-added language propaganda technique. And the last one is detecting absolute pronouns like everyone, everything for bandwagon propaganda technique. In order to do so, I have composed a few lexicons in TXT format containing lists of glitter words, intensifying adjectives and adverbs, absolute pronouns, and computed corresponding coefficient for each sentence in the dataset by counting the matches, the number of matches, and dividing them by the total word count in the sentence. For vectorization, I have used a model that is called Word2Vec. It's a shallow-to-layer neural network which is trained to reconstruct linguistic contexts of words. It takes as its input large corpus of words and produces a vector space, typically of several hundred dimensions, with each unique word in the corpus being assigned a corresponding vector in the space. To extract vectors, I've used a pre-trained Twitter 200-dimensional model to extract features, and for these purposes I've used GenSim Python library. The next thing I do is part of speech tagging. It's a technique that allowed me to make my text data more specific, so vectorizing is more specific as well. It's replacing words with our dataset with a word part of speech lemma formatting string. For these purposes, Spacey Python library is used. And I have also used grid search and logistic regression for the sentence level task after performing cross validations. Best parameters of the sentence model are penalty is also a ridge regression, solver is also LBFGS, and the C parameter is 7.74. The grid search is being refitted according to achieving the best F1 score of the model. So after training our data, our model score is the following. It's 0.74, and confusion matrix looks like this. It means that we accurately predicted 1,917 non-propaganda articles and 205 propaganda sentences, while 146 propaganda sentences and 585 non-propaganda sentences were misclassified. The libraries I used were scikit-learn, NLTK, GenSim, Spacey, Pandas, NumPy, Matplotlib, OS, Copy, and Seaborn. Thanks for your attention, and now I would like to get to demonstrating how my program works. So as we can see, this is the article level coursework, the article level model. As we can see, the data is being converted to lowercase. It's being replaced, the punctuation is being replaced, and the stop words are being removed. The next thing we do is we vectorize our data. Firstly, we divide it in test and train sets, then we vectorize, transform it, and fit our model. And so we can predict some of our